This video is going to be a review for the final exam for the data structures class this summer. So on the final exam, no programming. Okay, so I've got on the screen here kind of a listing of what I'm going to be talking about here. There's no programming. Instead, you're going to be solving problems and answering questions about pros and cons and definitions and why we'd use this versus that about the data structures. Okay, so solving problems here doesn't mean creating a program. It means using the data structures, drawing the pictures or whatever to use the data structure to solve a problem. So the example I give here, if you're given an array of numbers, okay, you've got 5 numbers, okay, then you want to reverse that array. So what we could do, we could push each element starting at the beginning onto the array, okay, or into the stack, and then pull them back off, basically. So you would just need to show pictures of the stack at those various positions, okay? Could be the same way I could ask you if you have a linked list of 5, 10, 15. I want you to insert 7 between 5 and 15. So using drawings on paper or on Notability or whatever you want to do on your iPad, but using diagrams, you would show a diagram of how we've been drawing a linked list and then show the connections where the new node would be created and how you would link up things kind of that way. So kind of like an algorithm, kind of like not programming, but show how the data structures would work. Okay. So that really is the point of this exam, is do you understand the data structures and what they're supposed to be doing for us as apart from the programming. Okay. So again, I would use either Notability or something that you can draw on your iPad and save that as a PDF and send it to me, or just do it on paper and then take pictures of it, send those to me. Either one should be okay. Okay. So all of these data structures may be compared with the arrays we've already done. Okay. So arrays have some pros and cons that we've talked about. Okay. So the first data structure we talked about were linked lists. Linked list can either be a singly linked list, could be a double linked list to go back and forth, could be a circular linked list. All those things should be able to draw all those. Okay. And the advantage to a linked list is that it's more efficient memory wise than arrays are, because and they're unlimited in size depending on the memory of your computer. So you don't have to know in advance how big they're going to be. Okay. The disadvantage is that you don't have direct access to any element. You have to begin at the beginning and kind of go through. Okay. Then we talked about stacks. Stacks have the property that the first thing into a stack is the last thing out. Okay. So there's oftentimes we want to use that to get the most recent thing first when we pull things back out. Okay. Then we have queues, which are just the opposite. So a queue, the first one in's the first one out. So that has a lot of uses as well. Okay. And then we have trees. Trees basically are nodes that have children that form a hierarchical structure. We most often use binary trees, which just means there are 2 children up to, so 0, 1, or 2 children per each node. Okay. Binary trees are difficult to write because if you're just inserting one, where you're going to insert it at, there's a lot to keep track of. So instead we tend to use the binary search trees, which have the property that for every node, all of the left children and grandchildren and great-grandchildren are smaller than the node, and all the right children and grandchildren and so forth are greater than the node. Okay. So they're called binary search trees because they help us if we go to search to see if a piece of data is in a tree and we get to the first node and it's a 50 and we're looking for 100, then we know if the answer is going to be found, it's going to be to the right. And we've immediately eliminated up to half of the tree, or up to half of the possible values, depending on how things work. Okay. What I didn't put in here that we should think about, because we've talked about it, is going to be searching, binary search, some of the other searches. There's not going to be much about merge sort and quick sort, because those play a much bigger part in algorithms, which is the next class that you take. Okay. So the binary search trees are very important for searching. The problem with binary search trees, if they get unbalanced, okay, as a simple example, if you insert 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 into a normal binary tree, you're going to have not a tree, but a stick. Okay, it's 1 will have a right child of 2, which has a right child of 3, and so forth. Okay, searching on that tree for 7, for example, has no greater efficiency than searching anything else. You're just doing a linear search, sequential search. Okay, it doesn't help you at all. So what we want to do, there are several possibilities to that on how to have what are called self-balancing trees. Okay, and the one we talked about in particular are the AVL trees, which are some people's names. Okay, so the AVL tree has the property that you create this balance factor, which is the number of left children minus the number of right children for each node. And we can only have valid values of 0, 1, and -1. Okay. And this is in the book, and it's also, there's a video about this. Okay. So we have 4 operations to keep these together. We have a left rotate and a right rotate. Okay. When things are in a straight line, too many items. But when they're kind of what I would call a dog leg, you have to do either a right left or a left right rotation. And that allows us to maintain this tree where it's never off by more than 1 on the different heights. Okay. And then we also talked about B trees just a little bit. B trees and graphs we hit just in video. We did 1 B tree program, but no graph program. Okay, so the B tree, the idea is we can have multiple values in each node. Okay, so we can have a 5-way tree, 10-way tree, whatever we have. And what this allows us to do is basically like indexing. So the example that I like to give, if you're going to use an encyclopedia, if those things still exist, if you wanted to look up flags, you wouldn't have to begin at the beginning of a gigantic book. You would go to the F volume. Okay, so that's kind of how the B trees work, and that you have these larger nodes with multiple values, and each value has, so each node has 1 child link for things that are less than anything in the node. And then you would have links between each of the 2 values to say, so if our node had 10, 20, 30, okay, there'd be a link to the left of anything less than 10. The link between 10 and 20 would be things that are greater than 10 but less than 20. All the way over to the far right link, which is greater than anything in the tree, and each node, or in the node, and every node is sorted. Okay, so B trees turn out to be used a lot more than the binary search trees, simply because there's so much data in the world to keep track of. The B trees do a much more efficient job of, instead of breaking it into half and half and half, it breaks it into pages of information. Okay, so those are very important. And again, we just don't hit them enough in this class. Okay, then we talked about graphs. Graphs turn out to be super helpful in computer science. You'll hit them in some math class, probably discrete mathematics, I would guess. So this won't be the only time you see them, but for this exam, make sure that you know the basics, that a graph is a set of vertices and edges, and there are different ways we can configure those. We could talk about being complete graphs, incomplete graphs. A cyclical graph is one that has a cycle where you can go from a node back to that same node. There are directed graphs which have arrows. Undirected graphs have no arrows, and both directions are allowed. We talk about a spanning tree and a minimum spanning tree, or some terms that we use. Again, not going to get heavy into that onto this exam, because all of that stuff will come up again in algorithms. So just doing a preview. So if you have the basics of the operation of a graph for this exam, you should be good. Okay. And then the standard template library. So let's talk about the schedule for this week. I'm putting this video out on Monday. So tomorrow, Tuesday, is the last day of class. So we don't have a full week this week. Okay. So instead of giving a standard template library program assignment, which I would normally do, I think you already used standard template libraries on the stack homework the first time through. So you're already familiar with the idea. So we're not going to cover another program. But you do want to look through the chapter in the book. And again, the development of the standard template library, and there's a video on that as well. The standard template library was developed because prior to that, the data structures you had to create yourself. Okay. Other newer languages such as Java had built-in data structures galore. Okay. So it was hurting the market share somewhat. So there was this idea that we're going to create the standard template library, which allows us to have some built-in things. Okay. And I think as we had talked before, students often ask, well, why don't we just use that instead of creating them ourselves? Well, and it turns out there are some good reasons to learn how to create them yourself. The first is that you get a much more detailed knowledge of how the data structures work when you have to create them yourself. Okay. And the second thing is that the data structures from standard template library or those in Java or anywhere else are kind of one size fit all. Okay. So it's often the time when you're going to want to do something different, something more custom. Okay. In particular, if you're working coding for a company, they're going to want a competitive advantage of some sort. Okay. You can't really get a competitive advantage if you're using the exact same tools that everybody else is. Okay. Everybody else is using. So if you can have the ability to create your own data structures, you can customize that library feature to be exactly what you want. So your data structures are much more efficient. So that's the basic idea. Okay. So that exam will be on Wednesday, and I will send out a separate email, and we can figure out a time to take it. I'll probably just, whenever you can take it, we'll hop on Zoom. I'll throw it out there. I'll be there for questions, and we can go from there. Again, either do it on Notepad, not Notepad, do it on your iPad in Notability or something where you can draw and write, or do it on paper, either one, and send me photos. Okay. But that'll be a live exam in essence. Okay. So I know you've struggled with some of the programs, with a lot of the programs in this second part of the class. Okay. And I'm not 100% sure what's going on. I've looked through your code. It looks like some relatively minor things are getting you in trouble. One thing I will say that maybe I said before, maybe I didn't, I don't know, I should have said before. Whenever you have an error, or actually should have been in your C++ class, whenever you have an error, and I'm not sure JGrasp works, it may be that you never actually compile in the same way, so you never see the errors in the same way, but certainly on the Linux compiler, whenever you get a whole page of errors, which is not unusual, you always want to find the first error. Solve the first error, it often solves a whole bunch of other errors. Okay. And there's kind of a trick to learning how to read the Linux-based C++ error messages. They're better than they used to be. Okay. The other thing you can do, if you find that first error, and you can usually scroll back up through the page on whatever program you're using to find that first line of errors. Okay. You can sometimes Google in quotes what that error message says and learn to track down what's going on. Okay. You'd mentioned the debugger before, and what the debugger, and I put a video out on that. What the debugger does for you is if your program's having a segmentation fault and you're not sure what line is causing it, it will tell you exactly what line is causing it. That's really all that does for you as far as we've been using it. Beyond that, you just have to go through and line by line see what's going on. One other thing that I would say, whenever you're writing a program, again, this class is weird because it's summer and it's fast and there's so much code to write. We tend to use code from the book, but even when you're doing that, any program I write, I like to write a small part of the program that's self-contained, then compile it, and then write a little more, and then compile it. By doing it that way, you have a better idea of at what point the error occurs. Okay. And again, this book doesn't really lend itself well to that. And that's unfortunate. And summer's hard as well. But those are some basic guidelines as to what's going on. Okay. It's kind of a different mindset than programming on the PC is. And both have their uses, both their jobs in both. So you have to kind of know how both things work. Okay. So it's about 11 o'clock now, and you said that you wanted to Zoom this afternoon. So if you see this before we Zoom, we can Zoom. 1:30 should be fine with me as far as I know. I'll let you know for sure when it gets closer to time, but it will be sometime this afternoon. Okay. If you have any questions on this, let me know. And I'll send out an email as well, asking you what time on Wednesday you would like to take the exam.